Welcome to our GIA Knowledge Sessions. These are a series of talks and seminars about gemology, and they're all fueled by our decades of research. And we're so excited to be able to have this platform to share them with you, since it's our mission to share all of our discoveries and learnings with the world. So I'm really excited to kick things off today. I'm Kelly Giordano, a member of the content team here at GIA, and I'm joined by Nathan Renfro, who is the manager of colored stone identification, and he's going to give us a very inside look into gems today. So before we get started, just a bit of housekeeping. Everyone attending this is automatically on mute, but if you do have a question, please submit it using the Q&A feature at the bottom of your screen. We will have some time with Nathan at the end to answer some of your questions as much as we can get to, and feel free to ask as we go. So if you have any questions as we're going, just pop them in the Q&A. The little people box where you see me right now and where you'll see Nathan in just a minute can also be moved around if you prefer, just in case it's blocking any of the presentation. You can just click and drag it around to different parts of the window. And we'll also be sending you a recording of this session either later today or early tomorrow morning in case you want to rewatch or send to any of your friends. So that email that will send you a recording will also have a survey. So we'd love to hear your feedback. And with that, I'm going to pass you over to Nathan.
Hi, everyone. So today we're going to talk about my favorite subject with regard to gemology, and that's the microscopic world. So the reason why I like the micro world of gemstones is it's a way you get to kind of be an explorer, an adventurer. When you look in a microscope into a gemstone, you may be the first person that's ever seen what is inside that stone. And many times I've looked in stones and seen some really strange and amazing things. And it's a way you can kind of be an explorer. And if you're like me and you would rather not walk through a jungle or ride on a rocket ship to the moon or something, you can still be an explorer from the comfort of your home, maybe even in your pajamas late at night, which is where I'm often looking in stones. And so it's just a fun way to be an explorer and see a lot of really neat stuff. And I've focused a lot of my work on photomicrography. And the reason why photomicrography is important is it allows you to take your friends on your adventure with you and share the things that you've seen. So so today I'm going to take you all on a bit of a tour of the things that I've seen in my microscopic adventures here. So to start, we'll talk about our vehicles. So if you're an astronaut and you're going to the moon, you're going to ride on a rocket ship and have a space capsule. But for us, we're going to use a microscope. The image on the left, that's the microscope that I use at home. It's about 35 years old, still does an excellent job. I use it almost every day. And then the microscope on the right, that's the one that you see here behind me. It's one here at work, and it's got a little bit more features and bells and whistles and automation, but that just kind of shows you, the evolution of the microscope in the last 30 or so years. Both work great. You don't have to have the one on the right. You can certainly get by with a 30-year-old microscope, no problem. Anyway, that's the basic equipment that we're going to be using. You also need some accessories like you see in this image at the right, fiber optic illumination, and you may have some diffusers and lighting control options there. Here's a few other of the accessories I use for photomicrography. On the image on the left, you have to have some things to clean your stone. If you take pictures of a dirty stone, you'll certainly take pictures of the dirt, so it's best to get the dirt out of the way. The image at the right, I have a stone holder here, which is what I use to maneuver the stone and put it in the right position and have the right angle for viewing. I'll also use these film canisters here. You can see that they've been modified and kind of cut in certain ways. And I use those to control the light so you don't have anything that's overly bright, and that diffuses the light, gives you a nice even illumination. I use polarizing light quite often, and so you can use a single polarizer between the microscope objective and your stone, and that'll show you differences in the pleochroic colors, and it also eliminates birefringence in doubly refractive stones. And then I have this black material here, which is really, it's a piece of aluminum foil that has this matte black coating on it. It's called cinefoil, and we can use that to block out hot spots or areas in the lighting that are too bright. And then all of those things are resting on this tablet here, and the tablet is sort of what we can now use in the digital age for editing, and we can talk a little bit about that later on. For editing photos, you know, if anybody has any questions in the Q&A about that, we can go over that. But all my photos are edited in Lightroom and Photoshop, and you know, a lot of people don't really look, you know, maybe understand that we don't edit photos to make them look better than they really are, but the photos get edited so that you can actually get the image to look as good as it does in the microscope. Here's a few examples of lighting control. This is how I would use one of those film canisters. So it makes just like a little microscopic light tent. And here, this black piece of foil, it makes sort of a shadow edge, so you can improve the details that you see by using a shadowing technique. And this is just an example of using a oblique fiber optic source for a reflective subject, and then a polarizing filter on here to control doubling. Focus stacking, this is another thing that's sort of an advancement in microscopy that's come about in the last few years. A lot of times we're looking at these three-dimensional objects and you can't see the whole image in focus at the same time due to the limitations of the lenses that we use. So the workaround for that is we take a series of images at regular intervals, and we can digitally stack all the in-focus parts of each image together into one fully in focus image. So here you can see the foreground is in focus, but the background fluid inclusions are blurry. And here we have the reverse, where the background inclusions are in focus and the foreground's blurry, but then when we combine all those together, we can get everything in focus. And this is how I do this at home. I have just a little measuring device attached to my microscope mask, so I can measure the step interval precisely, and then using a program called Helicon Focus, it will assemble all the images together. Specialized microscopy. This is the microscope we have here at GIA, which is a compound microscope outfitted with hardware for a technique called differential interference contrast. That's how we produce these sort of bright, colorful surface photomicrographs showing high contrast and vibrant colors in otherwise low contrast subjects. This microscope is about 10 years old. And then this is the one I have at home. This one's from about the 1960s, and they both do the same thing. If you want more info after the talk about inclusions and photomicrography and how to take photos and what are the inclusions, inclusion identification, things like that, there's a lot of resources that are available. There's certainly 80 years of Gems in Gemology and also the Journal of Gemology. In those two publications, there's several articles on identifying inclusions and you know, what certain types of inclusions are. We have a Microworld column that is produced in every Gems in Gemology issue since 2015. And so that just highlights sort of unique and interesting inclusions. For diamonds, there's the book by John Cuevila, Microworld of Diamonds, and also you can't have a talk on inclusions without mentioning the Photo Atlas series of books by Edward Gubin and John Cuevila, which are, you know, just massive and have, you know, identification of more inclusions than you can imagine. So let's get started on our journey here. The first stone we have here is an insect in amber. As a kid, I was a big fan of the Jurassic Park movies, so I certainly love looking at amber and seeing what kinds of remnants of bugs and things like that are present. Kind of brings your imagination up for, you know, the way life was hundreds of thousands of millions of years ago. This one's from the Dominican Republic, and it's just kind of an interesting insect. I couldn't tell you what type of insect it is. I'm not an entomologist, but it's certainly interesting bug, that's for sure. These are some etch tubes in a Heliodor beryl from Russia, and in the beryl, when it was growing, it had these dislocations in the crystal lattice, and then subsequently the stone underwent a dissolution phase where the surface started etching, and the etching or dissolution occurred more rapidly along the dislocations in the crystal lattice and produced these kind of squiggly etch tubes. And it just so happens that the etch tubes were the right thickness to produce thin film interference colors, so that when you light it with oblique fiber optic illumination, you get these sort of rainbow vibrant interference colors. Here's another beryl. This one's an aquamarine, and it has a skeletal ilmenite exsolution crystal, and these commonly occur parallel to the basal plane of the crystal, or perpendicular to the optic axis. And so they're all crystallographically aligned, and so when you light them up with fiber optic illumination, anything aligned in that plane is going to light up kind of brightly, and it has this sort of coppery sheen to it. But in bright field, these inclusions are typically black. This is a fun inclusion in a red beryl from Utah. I don't know how many of you saw the Neowise comet here recently, but it went around and made quite a bit of news. But this one is a comet-like inclusion in a red beryl. And so there's these little stringer-like, needle-like structures that nucleate off of this, what is probably a quartz crystal. Here's another beryl. This one has a spiral-like tension crack. Now, the cause of these spiral-like cracks isn't really known, but there's something in the growth that is causing strain, and the strain gets relieved by cracking, and the crystal structure is what's controlling or defining this sort of repeating pattern here of cracking. This photograph was taken with some specialized contrast illumination called RHEINBERG illumination, and that's where you basically have multiple light sources, and each light source you use a colored filter in front of it. And so I have transmitted light with a blue filter, and then I have fiber optic illumination coming in at a different angle with a red filter, and that lets you highlight different features of the stone so that they stand out in high contrast. Otherwise, this beryl is sort of a near colorless pale blue aqua. Here's another example of RHEINBERG illumination. This is an etched surface of a beryl crystal. So again, I have transmitted light directly behind the stone that is with a blue filter, and transmitted light from on the sides of the blue filter is red. And so you get this sort of high contrast color combination in what would otherwise be a pretty pale, low contrast stone. Another aquamarine, we have these thin film fluid inclusions, and just like the ilmenite from a few slides ago, these fluid inclusions are oriented parallel to the basal plane or perpendicular to the optic axis, so they're very directional. And these, each of these little patches of color is an area where fluid from the growth environment has been trapped by the host aquamarine, and they're thin and platy in their structure, and they just happen to be the right thickness to produce thin film interference colors. And depending on the thickness of each of these little localized areas is what's controlling the color that you see. So different colors would correspond to different thicknesses. This is a beryl with tourmaline, and you know, I really like gemstones to have other gemstones in them, and this one's no exception. Sometimes you get birthstones and birthstones, which is fun, and we'll talk a little bit more about that in a few slides. But this one had some of these nice green tourmaline crystals in this colorless beryl. This one was from Brazil, I think. And along the interface of the tourmaline and the BERYL, you also get vibrant colors due to thin film interference. You may have noticed from the example so far that thin film interference is quite the way to produce a lot of interesting effects and colors. Nailhead spicules in a synthetic emerald. As gemologists, it's important to look in the microscope because there's a lot of synthetics and treated stones. And so just because a stone's synthetic certainly doesn't mean that it's not interesting. This synthetic emerald was grown by the hydrothermal method, and it has what's commonly referred to as nailhead spicules. And what these are really growth blockages where you have something at that would be the nail head. Like here, it may be a small cluster of phenakite crystals. And once those precipitate out and the crystal is growing, which it would be growing from the top to the bottom in this direction, these inclusions block growth directly behind them from being able to crystallize emerald in this immediate vicinity. So what you wind up having is a void here, and the void gets filled in with the nutrient solution that you're using to precipitate the emerald with. And so as you have rapid growth in this top to bottom direction, in the case of this stone, you have this void filled in with a contraction bubble and some fluid until eventually the growth catches up from side to side in order to close off or seal in this tapered void. So just a fun example of nailhead spicules. This is a fun stone in Chalcedony that had these strange lime green inclusions, and this material's from Mexico. And recently I was able to identify these with Raman spectroscopy, and it turns out that they're a mineral called CONICHALCITE, which is, I think it's a copper arsenic mineral. This was a kind of an interesting inclusion in a chalcedony, this dendritic agate, and it reminded me of sort of a reflection of a lake with a tree line, forest, and some low mountains on it. But this is actually an escape tube where you'd have fluids escaping in an agate, and then you have this intrusion of manganese oxides or pyrolusite that form these dendritic structures. But one of the interesting things about this particular stone and some of these types of agates is that they have this slightly yellow appearance, but then when you heat them up in the well of your microscope, they change color. And so here's what the stone looked like after heating for a couple minutes in the microscope. And then after letting it cool back down, it'll return back to the yellow state, which is kind of an interesting effect for some of these Brazilian agates. A few years ago, I got really interested in fossil dinosaur bone, and I would go to Tucson and try to buy interesting samples of dinosaur bone. Maybe it's in line with the amber from before and liking the movies Jurassic Park series when I was a little kid, but these fossil dinosaur bone, you have these really big hollow structures and open pores in the bone, and those get infilled with chalcedony, and you get these little miniature geode-like structures or agate infillings in there. And they have contaminants of iron oxides like hematite and goethite in there. And so that produces these kind of high-colored ring-like structures. And in this particular sample, it was a pretty thick slab, but I ground it down to just a little bit less than 1 millimeter thick. And then I put a blue filter behind it for high contrast to the metal oxides in here. And so I just thought it kind of made an interesting thick section, I guess we would call it. Here's another example of metal oxides in chalcedony, and this one produced these kind of spire-like structures, is what it reminded me of, sort of a futuristic cityscape. But in reality, the way it would form in the ground is this way. And so as you have the banding from the chalcedony being formed by horizontal deposition of silica-rich fluids in a sedimentary process, occasionally you would have layers that would have metal oxide contaminants. And the metal oxide contaminants are going to be more dense than the silica. And so before this whole structure solidified, you would have gravity pulling these metal oxides down through the silica-rich gel until eventually it cooled down enough to solidify and freeze these metal oxide structures in place. Many times we see things in gemstones in the microscope that look like other things that we're familiar with, either objects or animals or plants in the case of this one. And so this was a chalcedony that had these goethite sheaves in it, and it just certainly looked like a wheat field or something, which was kind of an interesting view in the microscope. This has got to be one of my favorite chalcedonies, and this is an iris agate. And so when you illuminate this stone from behind, you get all this wonderful rainbow colors. And it's got a layer of crystalline quartz along the bottom that reminds me of a frozen lake. And then these manganese oxide plumes look like the tree line of a forest, with overhead what looks like the Aurora Borealis. The back of this agate was sort of creatively carved and produced this sort of swirling pattern, which gave a little bit more interest into the colored pattern, made it more like the auroras. But certainly one of my favorite agates that I've ever come across. All right, on to diamonds. So this diamond is particularly important to me. This is a stone that was given to me by my mentor, John Cuevila. And the reason why he gave it to me was because I was planning to use a diamond to propose to my now wife. And so this is actually my wife's diamond. It was shown on the GIA Instagram page a little while ago. But the great thing about this diamond is it has a PYROPE garnet inside. So really neat inclusion inside of a really neat diamond. And this stone, I always talk about interesting clarities. You know, this stone is a Si2 in clarity, but to me, it's certainly much better to have a garnet creating an Si2 clarity grade as opposed to a crack in your diamond that gives you an Si2 clarity grade. But if you were in a jewelry store and you had this Si2 stone, you might have a customer that comes in your store looking for a diamond, and maybe they don't want such a low clarity as Si2. But let's just say that you had a mother whose birth month was April, and she had a child whose birth month was January. Well, this stone would be the perfect fit for them, because you'd have the birthstone for April, which is diamond, and the birthstone for January representing their child as the garnet inside. Now, fortunately for me, my wife, her birth month was in April, so I had that part covered. And then when we had our first child, he was due to show up in February, and in the middle of February, and I thought, well, maybe he might show up a little bit early and make this diamond work out in his favor so that it represents him and his mother. Well, he did show up early, but he came at December 28th, so he was just a little bit too early, and so he missed it by about 3 days, but it worked out okay anyway. So anyway, this is just a fun stone of birthstone, or fun example of birthstone in a birthstone. This diamond is quite an interesting stone that went a little bit viral on the internet a while ago, and it was termed as the MATRYOSHKA diamond, which is the Russian nesting dolls, and that's because there's a diamond inside the diamond. And what's great about this diamond is that the interior diamond is in an open cavity and is free to move around. So what I did was I took several photos of this stone and I aligned them in such a way that I could position the host diamond in exactly the same spot. But then it would show the internal diamond, how it's able to move around in the cavity inside. So just sort of a fun stone. The diamonds with mobile inclusions are quite rare, but certainly this isn't the only one that we've seen. This kyanite diamond was really a spectacular stone. A friend of mine had alerted me to this stone that they had, who I went to GIA with, Anna Samsonova, and she told me about this stone. And so we were able to get it and examine it, and we identified this inclusion as a kyanite. And this is just really a huge kyanite crystal inside of this diamond. And it's just really beautiful, and you have this, in polarized light, you have a lot of this strain. So whenever you have a brightly colored crystal inside of a diamond, even though the clarity is significantly decreased, there's a stone like this is much more rare and significant, in my opinion, than a high clarity stone that would be otherwise kind of boring to me. Here's another example of a diamond with a mobile inclusion. And this one was kind of interesting. You had this, looking at it from the inside out through this polished face, there's this kind of negative crystal cavity here, and it has this green radiation staining on it where you had radioactive fluids enter that cavity and modify the color. But if we look at the stone from the other side, what you see is that this small opening you can see a small diamond through this even smaller opening. So this diamond inside can't escape through this hole or this opening, and it's trapped in this cavity. And the interface between this included diamond and the host diamond was dissolved away as the stone was transported to the surface, just enough so that it allowed some space for this diamond to rattle around. So here I've done the same thing where I've taken several photos, had them animated into a video where I maintain the position of the host, but then get to see the inclusion move around. So here's what that stone looks like with the diamond moving around inside the cavity. Just kind of a fun stone. Here's a diamond that I recently shot. These stones are in the market. They're sold as asteroided diamonds, where they have these really dense hydrogen clouds and interesting patterns. This one was particularly unique because it had this long etch tube that reached all the way to the very center of the diamond. And so to me, what that looked like was a dandelion where, as a little kid, you could pick these and blow on, make the dandelion seeds disperse in the wind. And so I thought this was just kind of a fun stone that reminded me of that. The specialized microscopy that we talked about earlier on is called differential interference contrast. And this is an example of the result that you get. You don't always have to show high contrast with vibrant colors, but I happen to like that effect, so I often choose colors and color palette that I like. But this is the surface of a diamond from Greenland, showing an etch feature that most people are pretty familiar with, called trigons, which are just these triangular etch features that you get on the octahedral face of the diamond. And so using the technique differential interference contrast with a microscope outfitted with a Nomarski prism, you can get this kind of bright, colorful effect. This is a really fun inclusion. And when I first saw this stone, we really didn't know what this mineral was. This is in a diopside from Tanzania, and it had this, what's now been referred to as a whisker and wheel structure. And this turned out to be a new mineral, which was named in 2016 by John Jacek and Mike Rumsey and a few other researchers. And this just happened to be a particularly good example of this new mineral, which was 2016 Mineral of the Year, called merilonite. So far it's been found in tanzanite, diopside, and I think quartz, and maybe in another mineral or two. Anyway, just a fun stone with a really unique structure for the inclusion. These are these bright colorful platelets are hematite platelets, an ex-solution product in this oligoclase feldspar. And this material in the trade is known as confetti sunstone because the hematite appears to have a bit of a resemblance to confetti, which is not too hard to imagine. This was just a particularly fun, nice transparent stone. Here's another example of ex-solution where you have the ex-solution products crystallographically aligned in the host. And so this was a orthoclase moonstone. So it just made a nice contrast from the adulorescence from the orthoclase host, and then all these ex-solution platelets of an unknown material sort of aligned in there. This was a fluorite with petroleum inclusions. And one of the interesting things about petroleum in general is that it's quite UV fluorescent. And so I took this photo pair to show the difference in lighting between looking at the stone using normal dark field with fiber optic light, and then looking at the stone with a UV flashlight. This is the surface of another fluorite from England, from the Rogerley mine, and I made the details of this fluorite show up by using a shadow edge, and that's where I have a transmitted light source from behind this stone, and then I bring in one of those pieces of black foil and block part of the light, creating this shadow edge, and that's how you get this high detail sort of shadowed effect on the edge features of the stone. So this shadow edge, most people are probably familiar with, and when you look at a full moon versus a half moon, the difference in detail is huge, and that's when you're looking at a full moon, it appears kind of flat, but when you're looking at a half moon, all the craters stand out in high relief due to the shadow edge that's created. And so this is analogous to the half moon, where you have the shadow edge highlighting all the features. Here's another example of a gemstone in a gemstone. And so this one you have spinel and grossular garnet. This stone's from Sri Lanka. So if you had, now that spinel's a birthstone, if you were born in August and your parent was born in January, this might be kind of an interesting stone to represent your bond with someone special. Here's a grossular garnet from the Jeffrey mine in Canada. And looking at it in polarized light, you see a lot of high order strain. It's always important to remember when you're looking at stones in the microscope to look at them using as many different types of lighting as possible. And so that would include dark field, bright field, transmitted light, using a fiber optic light. And also one that's probably less commonly used is looking at the stones in polarized light. So a lot of times you'll see things in polarized light that you wouldn't see otherwise, and this strain is one example of that. Here's another garnet. This one's a color change pyrope garnet, probably from Tanzania. And just under the surface of the table, there's this large metal sulfide inclusion. So this stone was cut to highlight the inclusion because it was so prominent, which not all inclusions are bad. A lot of people like their stones to be completely clean, but I quite like the ones with something interesting in there, especially when they're cut to showcase that feature. Here's another interesting material. This is Slocum stone glass, which was manufactured by John Slocum back in the 1970s, before synthetic opal really came available on the market. And this particular one's interesting because you have all this metallic foil that has this sort of brecciated structure. So what that tells you is that the foil was basically inserted into the glass before the glass cooled down. And then as the glass kind of settled and pooled out along the surface it was being made on, the glass was flowing on a flat plane and stretching out in all directions, and basically shredded the aluminum or the metallic foil into these angular fragments. And then once it cooled down, it froze that new position of the foil in place. So it's just kind of a interesting photo of a manufactured material. Now this is probably the strangest synthetic that I think anyone's probably seen. This is a material called neodymium pentaphosphate, and it was an experimental material that was grown by the US government for laser research, but it turns out it wasn't a very good material for that, especially in manufacturing, because with some slight pressure, you would get this sort of plastic or elastic twinning that was reversible. So here's what the stone looks like in polarized light normally, and then when you squeeze it a little bit or a little bit more, you can see the change in this lamellar twinning. And I also have a video showing that in real time of what that looks like. So again, this is using polarized light to squeeze, and so my fingers are at the corners of the video, and so I'm just kind of squeezing and slightly twisting this stone, and you can watch the twinning develop and move throughout the whole stone. You have these hundreds and hundreds of twin planes that sort of come and go as you apply pressure. So this is just a really strange, interesting synthetic gem material. Not very much was made, so most people are likely to never encounter this, but you just never know what you might see in the microscope here. All right, so here we have a material known as star obsidian, and this material has sort of an aventurescent look, so it's kind of glittery or sparkly. And it has all these hematite inclusions that have precipitated out of the glass. So kind of interesting material from, I think it's from New Mexico. Here we have an opal. So this is an interesting opal from Ethiopia. A lot of people may be familiar with this sort of cellular digit pattern type structure that you get in opals. Well, it's common in opals from Ethiopia, but you can have it in opals from from Virgin Valley and Mexico, but it's certainly common in Ethiopian stones. And so you have these sort of individual cells here, and this one has all these little ruptures where it looks like the contents of the cell has kind of leaked out and preserved the sort of optic crystal structure here. So you still have play of color on these little leaked areas. And then you have in between the individual cells, you have a sort of non-phenomenal opal that must have been a second generation of opalization. But this is just a really strange structure where something has caused these cells of opal to rupture and leak their contents. Just kind of a strange stone. Here's another strange opal and kind of an interesting stone. This is an opal from Australia, and it had a fracture develop in the stone while it was still somewhat in the growth environment. And so this fracture allowed manganese-rich fluids to enter, and the manganese was deposited in the opal and precipitated out from the crack as these manganese oxide plumes or pyrolusite. So once it solidified, as the opal cooled down, solidified, you preserve these sort of metal oxide plume structures. This is another strange and unusual opal. This one's from Virgin Valley. And this material is called conch opal. It's pretty rare, and what it is you have opalized wood, but before the wood was replaced with opal, this particular section of wood was diseased and started to rot and deteriorate. It had a fungus that was attacking it and was creating all these pore spaces in the wood. And so this rotten wood was then subsequently buried, and hydrothermal fluids that are silica rich came in and deposited this opal in all these open pore spaces. And so you have the rotten holes in the wood that are filled with these bright patches. The rest of the wood, you still have the cell structure and the grain of the wood preserved and intact. So this is a really interesting stone from Virgin Valley. This is a very rare and weird quartz from Brazil. And this one has a large negative crystal or negative space here. And it's filled with a blue copper fluid. Now, your first impression of this is that the stone has some kind of dye in there, but this inclusion is completely sealed off and trapped. And so this is a copper-rich fluid that has filled in this open space. And there's a contraction bubble here, and this bubble is actually free to move back and forth throughout this open cavity, sort of like a spirit level. So just kind of a really fun stone with a vibrantly colored inclusion. Got a lot of blue fluid along the interface of these other quartz crystals. This is a mineral called Gerstorfite, which forms these sort of silvery octahedral crystals, and this one's trapped in quartz. It's I think it's a nickel arsenic sulfide, and so just sort of a real pretty inclusion. And then in the background here, this is a fluid inclusion that has thin film interference colors. So just sort of a interesting sort of intergalactic looking scene. This is papagoite in quartz. So there's the Messina mine in South Africa produces quartz crystals with a wide range of interesting inclusions. Papagoite is this brightly colored blue inclusion, and you also in the same deposit you have these sort of bluish green inclusions of aholite, and then you have emerald green inclusions here of a mineral called tangite. These yellow inclusions are epidote. So just kind of a fun, very busy inclusion scene in this quartz. This is really a strange inclusion in amethyst from Uruguay. And occasionally you'll get these sort of fluorite puffballs in these amethysts from this deposit, but this particular one has a very weird blue core area of an unknown material. Not really sure why it's blue. It's the only one I've ever seen like that, but just sort of a fun inclusion there. Pink fire quartz, this is material from Brazil, one of my favorite inclusion stones. And when you look at this material in reflected light, the covellite inclusions, which are copper sulfide mineral, I think, they are vibrant pink. And so you have this quartz that shows this pink, really intense evanescence using reflected light. But in transmitted light, all those inclusions are very much green. So you have, depending on the lighting environment you have a different appearance. This is an amethyst from Nigeria with Brazil law twinning. All your natural quartz is going to show Brazil law twinning, but in order to see it, you have to look at it sort of down the optic axis or parallel to the optic axis using polarized light. So this is what it looks like, and so it kind of reveals the trigonal structure of quartz. Even though quartz has sort of a hexagonal outline, crystal structure is trigonal, which is clearly seen here. This is a rutile star, and it's on a core crystal of HEMATITE-ILMENITE. And so rutile is the mineral made out of titanium dioxide, and hematite is an iron oxide, and ilmenite is an iron titanium dioxide, and they form a solid solution series. And so these core crystals serve as the nucleation point for the rutile. But what happens is, in the growth environment, you have this core crystal of the ilmenite, and in order for it to exist, it's depleting iron and titanium out of the nutrient solution or the growth solution, and then eventually it runs out of iron. And once it runs out of iron, you can no longer keep growing the hematite-ilmenite. And so what you're left with in the growth solution is an excess of titanium. So at that point, you have nucleation of a new mineral, which is the rutile, which serves as the core crystal serves as a nucleation point. And so you have these six-legged radiating stars, star-like structures that form as a result of nucleating on these core crystals of hematite-ilmenite. This is a synthetic quartz surface, and so you have this kind of textured growth hillock type surface. And I took this pair of photos by using that technique we talked about earlier, which is RHEINBERG illumination. And I used 3 colored filters because of the trigonal structure of the quartz. So I had basically 3 colored sectors that are all crystallographically aligned. And so I had a yellow light up here, and a blue light here, and a red light here, kind of as a colored filter behind the stone. And so that each section would really show the color that it's related to. So all the red sections are aligned with each other, all the blue sections are aligned with each other, and the yellow sections are all aligned with each other. So here's the same image, but instead of using colored filters for contrast, I used variations of black and gray and really white, or this very light gray here, to produce the same contrast. This is a stone that I recently was able to examine. It's this beautiful little delicate inclusion, kind of looks like a flower floating in this colorless quartz. From the microscope, it looks like it may be little blue needles of tourmaline, but I tried to analyze some of the inclusions with Raman spectroscopy, but they were too small to identify so far. So that one might need some further work to conclusively determine if that's tourmaline or not. Here's the same stone, but looking at it perpendicular to the previous direction using polarized light. What you see is all the little fine needles show bright, vibrant colors here. And there's a core crystal of quartz that these needles are growing on. And this whole assemblage is right in the middle, or the very core of the host quartz, which in polarized light, you see the BERYL law twinning here. This particular growth sector, the point of it is where the inclusion lies. So it just kind of made an interesting inclusion scene there. And that's all just done with lighting control and using polarized light. This is a pyrite sun. So this is what we would call an epigenetic inclusion. And so there's three terms that we use to describe the relationship of the inclusion relative to the host, and that's protogenetic, syngenetic, and epigenetic. Protogenetic inclusions, that's when you have the inclusion that existed before the host trapped it, and often those types of inclusions show rounded edges where they've undergone dissolution. Then you have syngenetic inclusions, and that's when the inclusion and the host formed or were growing in basically the same time. Those inclusions usually show sharp edges, well-defined crystal faces. And then you have epigenetic inclusions, and that's when you have the inclusion that formed after the host. Now, in order for an epigenetic inclusion to occur, in the case of this pyrite sun, it had to find a way into the stone. So basically you have the quartz had a fracture in it, and then iron-rich fluids entered the crack and deposited this, this pyrite radial crystal. And so it's formed in this flattened sun shape because it was confined to the fracture. And then the fluids also left behind or either partly decomposed some other pyrite and left these sort of iron hydroxide minerals, this limenitic staining in other parts of the open fracture. This was also the cover of the 2020 GIA calendar. This is an example showing pleochroism in an inclusion. And so this is a registered photo pair, and inside the quartz host is a mineral called axonite. This one is from the New Melones Dam in Calaveras County, California. And using a polarizing filter between the objective and the inclusion, you see the pleochroic colors of the axonite, which is quite pronounced. So you have this sort of purple color and this sort of golden orangey yellow type color just by rotating the polarizing filter 90 degrees. This is a fluid inclusion in quartz with carbon dioxide. And so when we're looking at inclusions, occasionally when we have fluid inclusions especially, we can change the temperature of the inclusion and you might have some sort of interesting reaction. In the case of this stone, just by cooling it down below 31 degrees or heating it up above 31 degrees will result in this bubble either appearing or disappearing. So if you heat it up, the CO2 trapped inside homogenizes into a gas, and then it turns into a gas, and so there's no meniscus for the bubble. If you cool it down, you have liquid CO2 in this compartment here, and then you have this sort of contraction bubble here, and this is the bubble edge. So occasionally you can get some sort of temperature dependent changes in inclusions in the microscope. Here's another example of using polarized light in a scapolite. This scapolite contained an apatite inclusion, and using a polarizing filter only just between the stone and the objective lens, we can rotate that and see the pleochroic colors of the apatite host. And then if we add another polarizing filter between the light source and the stone, so that the two polarizing filters are crossed, basically turning the microscope into a large polariscope, we get these sort of birefringent colors from the apatite. So there's a lot of ways to control the lighting to produce sort of a different effect in the inclusions you see. Here's another example of changing the lighting environment. These are dissolution tubes in a kunzite, which is a pink variety of spodumene. Just like the BERYL we saw earlier on, this stone obviously had some dislocations or defects in the crystal growth that were propagated as the stone was growing, and then the stone underwent a dissolution phase, which caused rapid dissolution along those dislocations. And so that left with these sort of ribbon-like tapering etch features. And using fiber optic light at an oblique angle, you get this thin film interference colors. Then using plane polarized light, we can see that there are all these birefringent crystals trapped inside the etch tubes, or these sort of ribbon-like structures, which would otherwise be kind of invisible. And that's represented by all these little bright specks that are confined in the tubes. That's some other birefringent mineral. Again, using fiber optic illumination from an oblique angle or diffuse light source or reflected light. This stone showcases quite well one of the most diagnostic inclusions in ruby. These are called thin film inclusions, and they're pretty diagnostic for Thai origin. So if you see this kind of feature in a ruby, pretty good chance you have a ruby from Thailand. Here's another example of a gemstone in a gemstone. So you have a sapphire host from Songea with a nice orangey garnet crystal trapped inside. Just a fun combination there. There's another example of a sapphire with another inclusion gem mineral trapped inside. This is a sapphire from Sri Lanka with a couple of purple or kind of violet colored spinel crystals inside. I've only seen two sapphires with violet spinel inclusions. One was in a yellow stone, and this one was in kind of a blue stone. So pretty rare inclusion, but still quite interesting. Here's another sapphire. This one's from Burma. And using reflected light, we see all of this, this finely textured rutile that is all oriented in the same direction, so it lights up at the same time. And these dark lines represent twinning planes in the sapphire. And so areas where you have twinning, you have these zones or these localized areas of high defect concentration. And because there's such high defect concentration, those areas can dissolve more of the titanium into the crystal lattice in areas without the defect. And so you don't get this precipitation of these exsolution rutiles in these twin zones. Here's an example of an inclusion and an inclusion, or a gemstone and a gemstone. But in this case, the inclusion and the host is the same material. So you have a spinel and spinel. And the interesting thing to point out here is that you don't really see the inclusion in this stone, but what you're seeing is the interface where you have the mismatch between the two stones. So there's probably a little bit of fluid trapped between these two stones, and that's why you're able to see this. But if you look in the areas where you don't have that interface showing, it looks like there's a hole here. And that's because the refractive index of the host spinel is exactly the same as the refractive index of the included spinel. So it makes the light travels through that stone and inclusion uninterrupted or unchanged. And so otherwise it's basically an invisible inclusion. And so whenever you see these octahedral type structures that stand out in high relief in spinel, those aren't spinel inclusions. Those are often negative crystals that are defined by the host spinel, but they're filled with fluid or carbonate or something else that makes them stand out in high relief, whereas a true spinel inclusion in a spinel is going to look very ghostly or nearly invisible like it does in this stone. This material became quite popular probably within the last couple of years. This is a GANITE from Nigeria. A lot of times they are sold as spinel or ganospinel in the trade, but the gemological properties and the chemistry matches quite well with GANITE, which is a spinel group mineral. And this particular example had this really nice orangey red inclusion of sphalerite. This is the surface of a tourmaline. This particular tourmaline is from Madagascar, and it's got, I used again used the black aluminum foil material to create this kind of shadow edge to produce a lot of high contrast in the surface of this tourmaline. It's sort of a fun edged surface. This is a dravite tourmaline with a really photogenic pyrite inclusion trapped inside. This pyrite's probably a couple of millimeters. It's very much eye visible in this stone. This is a crystal of sphene or titanite, and the surface of this crystal was really interesting because you had all this etching, but the etch pattern is not related to the host. It's related to a mineral that was on the surface and had been dissolved away. So these are little stacked surface and they're no longer there. And so you get all these kind of elongate, almost worm-like structures on the surface of this titanite. Here's another spiral structure like we saw in the BERYL a while ago. This particular one there's a few things going on with how I photographed this. So these spiral structures are usually really long, and so they're much longer than the camera sensor is formatted. So what I've done is I've taken a series of probably half a dozen photos to image each piece of this structure, and then I used Photoshop to stitch those series of images together in sort of a panorama, and so that you can see the whole spiral structure. And then the difference between the top and bottom images is that this is what the topaz looked like normally using just transmitted light. And so it's colorless topaz, but in order to highlight the spiral structure, I used the RHEINBERG technique where I use a blue color filter to illuminate the spiral structure in the core. And then I use a red contrasting filter to highlight the body of the stone. So just a really interesting spiral structure in that topaz. Here's another example of a gem in gem. This is a really pretty spessartine garnet in topaz. And like we were talking about the terms of protogenetic, syngenetic, and epigenetic, the fact that this garnet has these really sharply defined crystal faces and is in pristine shape, that indicates that this garnet is a syngenetic inclusion, meaning that the garnet and the host topaz formed at basically the same time. And here's another example of a garnet inclusion. This one is in a green metamic zircon. And so just a fun stone, and you can see this kind of planar structure. This is from the metamic breakdown of the zircon. So again, just another example of a gemstone in a gemstone. Then our last image is another zircon, and this one is a vincerescent zircon. So when you look at the table of this stone, you have this sort of glittery appearance or this vincerescence. And all these little discoid cracks, which kind of look like lily pads if you thought this was a peridot. And the difference here is that all these cracks are due to the radioactive decay that's actually decomposing the crystal structure of the zircon. And so that radiation damage from trapped elements like thorium and hafnium that are breaking down this zircon, as it decomposes the structure, it's creating a lot of strain, and the strain gets relieved by cracking. So you have all these crystallographically aligned cracks that are very reflective using oblique fiber optic illumination. Okay, and so that's our GEM journey for today, and that's just the kind of stuff that I look at on a routine basis. I think we have a Q&A session coming up here. If anybody has any questions they've submitted to Kelly.
We sure do. We have a lot of really great questions. So I might not be able to get to them all, but bear with me. That information was all fantastic. Those images. We got a few people asking if they can be repurposed as art, and I think they certainly can be. So stay tuned. So a few questions, starting off with part of what you talked about in the beginning of, dirty gems give you dirty pictures. So what are some of the cleaning items that you use, specifically the fluid that you use to clean stones before shooting?
Okay, that's a good question. I have, right here I have, for most things, I have this little bottle of water, and it's got a hole in the cap with just a little brush probe, and I can wipe the stone off with that. So this is just clean water that I use for the vast majority of stones. For diamonds in particular, diamonds are, they love to be dirty, and they're really hard to clean. Grease sticks to diamonds. And so for those, I use a bottle of acetone. So same thing, I use a brush probe, but I have to keep the cap on, otherwise the acetone will evaporate. So acetone for diamonds, water for basically everything else. Great,
that's easily available at least. Are there any key features that you would consider a microscope needs to have if somebody was going to do photomicrography at home?
Oh, sure. So the key features would be, if you really want it to be for photomicrography, the best feature is that it's a trinocular microscope. So what that means is you have the two oculars where your eyes go, and then there's a third port which is dedicated for the camera. You can still use a binocular microscope for photomicrography, but then what you have to do is your oculars get obstructed by the camera, so then you have to use your computer or your phone screen to actually observe what you're seeing. So it makes it a little more cumbersome to use. So the key feature by far is to use a trinocular microscope for photomicrography. Otherwise, just get the best microscope you can for your budget. That could be a brand new microscope, or that could certainly be a used microscope that is maybe cheaper but had good optics. So yeah, that's trinocular, that's the best feature.
Okay, and is there a particular lens or a camera that you like when you're taking these pictures?
So I am not really brand loyal at all, but I really like my Canon camera. At home I use a Canon 6D camera, but I use that on my Nikon microscope. So I don't know if Nikon would like that or Canon would like that, but that's the hybrid setup I have. But here at work, on this microscope here, it has a dedicated Nikon microscope camera, which is integrated into the software. So this is a whole microscope system made by Nikon. But yeah, I like my Canon camera. Any good camera that you can get on the microscope is going to be okay.
Okay, and what's the range of the magnification on a lot of the photos that you showed today?
So in general, at home, my microscope, the magnification range is a little bit lower. So it's usually between 10 and 40 power. Here at work, this microscope has quite a bit more zoom range, and so the magnification could go up as high as about 125 or so. So the images, the maximum or the smallest field of view that you would see in some of those images is just under 1 millimeter. And then they could be as wide as, 25 millimeters or so.
Okay.
So that's sort of the range. So quite a wide range on this microscope.
Yeah. Can you talk a little bit about the fluid filled spaces in diamonds? And, you know, if they're created under intense pressure, doesn't that seem like it should push any air bubbles out? So how do fluid inclusions form when diamonds are formed under such crazy pressure?
Okay, so fluid means that it could be a liquid or a gas. So just because it's a fluid doesn't necessarily mean that it's a gas phase in there. As far as the question of fluids relating to diamond inclusions, that's probably a question better left for Evan or some of our diamond researchers, but certainly diamonds do trap fluids. But as you have fluid inclusions form in gems in general, the pressure and temperature conditions that fluid gets trapped at the stone is different than the conditions that the fluid is when you're examining the samples. So if a fluid gets trapped at a high temperature, like in the growth environment, the higher temperature would allow that fluid to be sort of a homogeneous mixture. And then as you bring that stone to the surface and now it's in your hand and it's not in the growth environment anymore, the temperature has changed, or the conditions of that fluid inclusions has changed. And so that's when you get unmixing and you start to precipitate different phases out of that fluid. So that's when you can have a gas phase show up and then daughter solid crystals. And that's because you've changed the conditions that the fluid was trapped in.
Great. How are you able to identify the gems that are in inclusions, like the PYROPE garnet that you showed?
Good question. So there's a few ways that that we can identify inclusions. We use advanced analytical methods like Raman spectroscopy, and that's where we take a laser beam and we shoot the laser beam on the inclusion. And then we collect a Raman spectrum from the inclusion, which we match to a database of known minerals. So that's a really great and powerful tool, but it's not necessarily always possible to identify inclusions that way. If the inclusion is too deep in the host, we won't be able to get the Raman spectrum from the inclusion. And if that happens and we really want to identify the inclusion, what we have to do is destroy the sample. So in that way, you have to destroy the sample so you can get access to the inclusion, but that means you don't necessarily have the inclusion preserved anymore. But if you've identified one inclusion and it looks exactly the same as another sample, and you conclusively identified one, it's reasonable to assume that the other inclusion that looks like very similar is probably the same material. So that's one way, we use is advanced analytical instruments, and then other times we're making a judgment that, from observations in the microscope, that this inclusion has the same properties as an inclusion that we've identified with another means.
Great. Can you try and how do you estimate the size of inclusions? Is that difficult to do, or knowing the size of the host gem, can you do it fairly easily? So
it's not really, so you don't really have to estimate. I mean, we can directly measure the size. And so when we take a photomicrograph and we know what the magnification factor of the optical elements in the microscope are, we use that information combined with the physical dimension of the camera that we're using so that we know what the physical dimension of the parts of the image are. So if we have a photomicrograph at 10 power and the camera sensor measures 36 millimeters, that tells me that the field of view is 3.6 millimeters. And so if I have an inclusion in an image that's 3.6 millimeters wide, I can convert the length of the whole image down to a portion of the image to exactly measure what the dimension of the inclusion is.
Great. So we'll end. We're over time, so we have one more question. Sure. Did you get interested in photography first or in gemstones first? Like what led to the other?
So I was definitely interested in gemstones first, and I came to GIA in 2007 and then started working in the Gem Ident department. And that's where I became pretty well acquainted with John Cuevla, and he sort of showed me the ropes of photomicrography and inclusions. And so then because of that, I had to learn how to take photos. And so, so the photography definitely came second, gemstones first.
Great. Well, thank you so much for joining us, Nathan.
Sure.
If anybody has any other questions, please find us on Instagram, Facebook, LinkedIn, and Twitter. And thank you all for coming. And please join us again next week, where we'll be joined by Rose Tozer, who will share all of her knowledge about Russia's treasure of diamonds and precious stones. So we'll see you all again next week. Bye.
Thanks.